Okay, it looks like we're going. Question 1. A rocket-powered car is attempting to break the world speed record for speed on the ground. First of all, let's talk strategy. The ideal situation would be if I could pick a system of objects within which the total momentum doesn't change. Or I tell you what, let's do something a little different. Let's try a bar chart. Like it says, you can do the steps of the strategy in any order that works for you. So, in order to make a bar chart, we're going to have to make a choice of system objects. What we have is a rocket car with a rocket engine and a bunch of fuel inside the rocket. So just for fun, what would happen on this bar chart, and then from reading this question, I can tell that when the rocket is ignited, a chemical reaction occurs and the fuel exits the rear of the rocket at 2.1 kilometers per second. So we've got a mass of liquid fuel and the speed of the fuel after it leaves the rocket. So picturing this, I picture hit the button, fuel goes one way, and right away I'm getting the sense that the car is going to be going the other way. But let's pick, what if we pick fuel and rocket for our system? Now, any unbalanced interactions? No. I'm seeing surface and earth balanced. So I think we can, with this choice of system, there are no interactions, so that would mean no change. So let's just sketch out a bar chart. What can we find an initial moment during which we know a lot about the system?
Yes. What's at rest?
Yes, when the rocket car is at rest, we know that both velocities are 0. So when your velocity is 0, your momentum is 0. Now, look, we know 3 out of 5 bars. If we learn one more bar, we can fill in the last one, and then we know everything. So, are there any quantities we know? Yeah. When the fuel gets thrown out the back of the rocket, we know the speed at which it leaves. So it doesn't matter if it comes out a little bit at once, doesn't matter if it comes out all in one go. All that matters to us is that 105 kilograms of fuel, I tell you what, has gone, well, I'll tell you what, so we'll calculate that number in a minute, but we can determine that bar. That means we know the final momentum of the rocket car, right? And if we know the final momentum of the rocket car, it's an easy step to find its velocity. With me so far?
Yeah.
Now, this is not the only way to address this. I'd like to stress this. You can start this problem any number of ways, but what you need to come to is this choice of system and object. Velocity is 0 for both. And in the final state, this is some velocity this way, and the fuel is some velocity this way. We've got 105 kilograms of it moving at that very fast velocity. Let's try not to skip too many steps. This is 590 kilograms. The velocity is unknown. Let's pick it. Let's just for fun. Let's call this direction the positive direction. So this velocity is positive. Okay so far?
Yep.
So math representation. This plus this plus this equals this plus this. The final momentum of the fuel equals 105 kilograms times 2100 meters per second equals some large amount. Let's do the math. 0 equals 220,550 plus momentum of the rocket car final.
Which has to be the opposite.
Okay, so we end up with this negative number for the final momentum of the rocket car. Is that cool? Yeah, it's not only cool, it would have to be. If the fuel has positive momentum, the car has to have negative. We know that from the definition of momentum. Tell you what, let's calculate this over here. The final velocity of the rocket car equals 220,500.
Is that the momentum?
Yep. I'm using the momentum to calculate the velocity, right? This calculation comes out to about that. It never hurts to label your answer with the symbol and highlight it. Is this reasonable? Well, this is a very high number. But if you, yes?
How did you get the really high numbers? How?
This number here. The question is, how did we get the initial momentum of the fuel? Momentum of the fuel, sorry, the final momentum of the fuel is equal to the mass of the fuel times the velocity of the fuel. And if you did not get a very large number, you failed to convert 2.1 kilometers per second into meters per second. Do you remember 2.1 kilometers per second? Did they torture you with this in chemistry? Stacking fractions to make this conversion? To get rid of kilometers, we need that on the bottom. What makes this fraction 1? Well, 1,000 meters on top and 1 kilometer. That's how you can do that conversion and get this initial velocity here. Final velocity, excuse me.
Is it negative? Is the final velocity?
Good point. Yes, because of this negative sign here, we need a negative sign here, which produces a negative velocity here.
Wait, what is velocity?
V for velocity, R for rocket car.
That's like the answer should be
What's P, R, T, and T or F?
It's supposed to be an F.
So what is that?
P for momentum,
No,
R for...
No. What is that equation?